Generating one word of text in a modern AI requires billions of mathematical operations, executed across a silicon processor in a fraction of a second. Early neural networks processed language sequentially from left to right, causing the numerical representation of early words to decay. The transformer architecture bypassed this by processing entire blocks of text simultaneously, allowing every word to interact at the exact same moment. The original design used an encoder to read data and a decoder to generate output. Modern models like GPT and Llama discard the encoder entirely. By focusing strictly on predicting the next token, the decoder-only architecture forces the network to develop internal representations of syntax and logic to satisfy the statistical requirements of the training data. To understand how these models function, we must build a modern decoder block from first principles, examining the specific calculus required to maintain a signal across hundreds of layers of silicon. The backbone of the transformer is the residual stream, a central data highway running straight from the input layer to the final output. If you push data through hundreds of complex sublayers, the numerical values and the gradients used to train them tend to shrink toward zero. This is the vanishing gradient problem, which prevents deep networks from updating their weights. The solution is to ensure the original input x is never replaced. Each sublayer simply adds its output, f of x, to the original stream. Y equals x plus f of x. The derivative of this operation is 1 plus f prime of x. That 1 ensures the gradient can travel back through the network without disappearing. Before data enters a sublayer, it passes through RMS norm. This stabilizes the data's numerical distribution based on the root mean square of its elements, maintaining a consistent scale across the model while saving compute cycles compared to earlier normalization methods. The combination of a protected derivative and strict numerical normalization allows the network to scale to hundreds of layers with stable signal fidelity. Because the network processes all words simultaneously, it has no inherent concept of word order. Without this mechanism, the cat ate the mouse is indistinguishable from the mouse ate the cat. Early solutions added static sine and cosine waves to the data, but modern models use a geometric approach. Rotary positional encoding, or ROPE, rotates a word's vector in a 2D plane based on its sequence position. Calculating the dot product between two rotated vectors measures their relative angle, revealing the precise distance between the tokens. ROPE embeds a spatial map into the model's math, allowing it to differentiate between identical tokens based solely on their relative distance from one another. Once positioned, data enters the core mechanism, self-attention. This is where tokens scan the rest of the sequence to collect contextual information. In the sentence, "The tiger is hunting because it is hungry," the model must identify what it refers to. The word splits its representation into three roles: a query looking for context, a key offering identity, and a value containing the actual semantic data. The word "it" acts as a query, comparing itself against the keys of every other word. When it matches the key of tiger, the vectors align, producing a high numerical score. However, in high-dimensional models, these scores reach extreme magnitudes. These large numbers push the upcoming softmax equation into a saturated state, where the gradient flattens and training stops. To prevent this, engineers divide the entire matrix by the square root of the vector dimensions. This forces the variance back to 1, keeping the numbers within a learnable range. Because the model is training to predict the future, it cannot look ahead. A diagonal causal mask overwrites every future word position in the matrix with negative infinity. Since e to the power of negative infinity is 0, the softmax filter assigns 0 probability to any upcoming word. The model is mathematically blinded to anything that hasn't happened. This process runs across multiple heads in parallel. While one head focuses on pronoun references, another might track verb-noun relationships. These distinct insights are then merged into a single vector. This dense calculation isolates the exact context of a single token from millions of semantic possibilities. This mechanism comes with a heavy computational cost. Because every word must check every other word, the operation scales quadratically. Long sequences of text can rapidly exhaust a GPU's VRAM. For models generating text one word at a time, recalculating the keys and values for every past word in the sentence is statistically redundant. To solve this, the KV cache stores previously computed keys and values in memory. For new words, the model only computes data for that specific token, reducing the computational load from a quadratic curve to a linear progression. However, very long sequences can still exhaust the memory. Grouped query attention solves this by forcing multiple query heads to share a single set of keys and values, significantly reducing the memory footprint. Ultimately, these critical interventions allow the model to operate within the physical constraints of standard hardware without losing any accuracy. There is a physical bottleneck on the chip itself, the speed of memory. Shuttling giant matrices between the large, slow HBM and the tiny, fast SRAM processing cores creates a delay that limits performance. This delay often forces the GPU's processing units to sit idle while they wait for data to be read or written to memory. Flash attention reorganizes the operation. By breaking the matrix into smaller blocks that fit entirely within the fast SRAM, the model can calculate its probabilities incrementally without constantly reading from the slow main memory. This doesn't change the final answer, but it optimizes operations to match the hardware's physical architecture, enabling much larger context windows. While attention connects ideas between tokens, the feed-forward network serves as the repository for factual information learned during training. Modern networks have transitioned from the rigid ReLU activation function to SWIGLU. Unlike ReLU, which drops to 0 instantly at its corner, SWIGLU has a smooth negative dip. This smooth curve allows for a finer flow of gradients through the network. It prevents the zero-state flatlines that often result in dead neurons, where a part of the model stops updating and loses its ability to learn. By expanding and then compressing the vector dimensions, this block extracts the specific factual data required to complete the layer's calculation. As the vector reaches the top of the network, it is multiplied against the language modeling head, a matrix containing every word in the model's vocabulary. This produces raw scores for every possible next word, known as logits. To turn these scores into probabilities, we pass them through a final softmax equation, which includes a variable called temperature, or T. When the temperature is low, the math exaggerates the highest scores, making the model more deterministic. At temperatures above 1, the scores are compressed, allowing lower probability words to be selected more frequently. The temperature parameter acts as a statistical lens, determining whether the model selects the most probable next word or explores lower probability alternatives. Specializing a massive model for a specific field, like law or engineering, usually requires updating billions of individual weights, an expensive and time-consuming process. Low-rank adaptation, or LoRa, uses a mathematical shortcut. Instead of updating the massive base matrix, we freeze it and introduce two much smaller matrices, A and B. Training only these small matrices reduces the total number of parameters that need to be updated by over 99%. The initialization of these matrices is specific. Matrix B is filled entirely with zeros before training begins. Because any matrix multiplied by a matrix of zeros results in 0, the fine-tuned model behaves exactly like the base model when training starts. This allows the model to retain its original capabilities while gradually learning new information through the smaller matrices. Once training is complete, the small matrices are added to the base weights, allowing specialized performance on standard hardware without increasing inference time. From the protection of the residual stream to the memory management of flash attention, the architecture of a large language model is a sequence of precise mathematical operations designed to maintain signal across a massive system. The decoder-only design is an engineering balance of variance control and hardware optimization, ensuring that billions of parameters can interact without numerical collapse. When we break down the transformer, we see that these models are not sentient black boxes, but rather pipelines of linear algebra and probability, designed to approximate the statistical patterns of human language.